Okay, this video is covering the idea of simple gears. Okay, so I have an animation here that I found on the Wiki Commons page of three gears that are rotating. Now let's think of the red gear, as being the driving gear. And so you notice that's rotating clockwise. It's forcing the blue gear, which I'll call gear B, to rotate. It's actually rotating in the opposite direction. Okay, and then gear B is driving the green gear, which is gear, I'm going to call it gear C. And again, that reversed the rotation, so it's got the same direction as gear A. All right, so some things to notice. This driving gear is spinning around at a certain rate. And notice this gear spinning in the opposite direction at a slower rate. Okay, and that's because the teeth here that link these together are exactly the same size. If they weren't the same size, they wouldn't mesh together very well. Okay, so this velocity has to be constant in here, which causes this to travel a slower distance. We have a further distance to make a full revolution, so it's rotating slower. Same thing over here, all right? The constant velocity of the intermeshing of the teeth forces this gear to have a slower rotational velocity. Okay, so we're going to talk about some of these things in detail, and I'm going to put a few numbers to these things, and we'll learn how to deal with some simple gear calculations.
Okay, now let's take this discussion to the iPad where we can talk about the formulas that describe the interaction for ideal gears. All right, so we have three gears here, but we're going to consider just two at a time. We're going to start with gear A and gear B. All right, and I'm going to put some numbers to this so that we can talk about it. Let's say that gear A has 10 teeth. So right here, 10 teeth. Let's say that gear B has 20 teeth. And later on we'll talk about gear C as well with 30 teeth. And since A is the driving gear, we'll start with some information about A. So we're going to say that torque driving gear A, so that could be through a motor, all right, is going to be 5 foot-pounds of torque. And the speed, the rotational speed of this motor or this gear is going to be 60 revolutions per minute. All right, so what I want to do now is take a look at gear A and gear B and look at the speed of rotation. Okay, so if you think about it, if you ran a gear for a while, let it start rotating, and you marked, if it was a wheel and you let it roll out, it would cover some kind of horizontal distance, based on the number of revolutions. Okay, so I could look at the distance traveled by gear A. If you unspooled it and rolled it out onto the ground, the distance traveled would be the number of rotations. Okay, so revolutions. So if I had 60 revolutions, all right, and I multiplied by NA delta X, right, delta X is the tooth length, all right, because I have NA delta X is a distance in each revolution. Okay, so that would convert that over to a distance. All right, so instead of using that 60, let's go ahead and call this omega A. And then we could do the same thing for B. Omega B I have a little problem because omega A is revolutions per minute, so let's go ahead and put per minute, and then we'll just multiply by 1 minute. So we'll get the distance traveled in 1 minute. Okay, that'll work for us. Okay, so if I have omega B revolutions per minute, and I wanted to know the distance traveled, it would be NB delta x. Remember, delta x is the same. The only difference between the gears is the number of teeth. And then I multiply it by 1 minute. All right, the minutes would cancel. And I would get this formula for the distance traveled if you treated gear B as a wheel and let it roll out for 1 minute. Okay? So because the teeth size are the same, all right, we should get the same distance between these two gears. All right, so I can equate dA and dB, and what I would have is WA times NA times delta x is equal to, I call that W, it's omega, it's an omega. Omega B times NB times delta x. All right, so maybe that was obvious to you, but the delta x's cancel and you get the difference between the speeds. I'm going to solve for omega B because I already know omega A, right? So I'm wondering if if gear A is rotating at a certain speed, what is gear B rotating at? Okay, so I solve for omega B and I get omega A times NA divided by NB. All right, so let's take a look at our situation here. We know that omega A was 60 RPMs, and then NA was 10, and NB was 20, and so it looks like the second gear is rotating at half the speed because there's twice as many teeth in the second gear. Okay, does that make sense? Hopefully that makes sense. Okay, we could apply this same formula to omega C, right? Because we know now that the gear ratio matters in terms of the speed. So if you want to look at the driven gear, all right, so omega C is the driven gear. You can multiply by the speed of the driving gear. The driving gear is gear B. Multiply by the number of teeth for B divided by the number of teeth for C. All right, in our case, 20 and 30. All right, so that means that you would take the 30 RPMs and you'd multiply by 20 and divide by 30, okay, which would give you 20 RPMs. All right, so that's the effect of those three gears in terms of speed. So you notice you could have looked at the gear ratio as a product, okay, so we would have had omega C is going to be omega B times NB over NC, but omega B was omega A times NA over NB, and so you notice the NBs would cancel, and you could have looked at the gear ratio between the two outer gears, all right? And what you would get is that omega A is, omega C, the speed, is omega A times NA divided by NC. So the 60 times the 10 divided by 30 gives you the 20. Okay, hopefully you're following that. These are the gear ratio formulas. All right, so now let's talk about torque. All right, so if I took a free body diagram of the red gear All right, so here's the red gear. Right? This has a certain torque and it's operating with a radius RA and it's generating a force because this is the driving gear. Okay? So tau A is known in this case, and we're assuming it's 5 foot-pounds of torque. All right, what is F? All right. Next, I could look at the blue gear. Okay. Here's our blue gear. It's got a different radius because it's got more teeth. It has to be bigger. All right, RB. And this has NB teeth. This has NA teeth. All right, so what we know is that this force interacting with gear B is in the opposite direction if you did a free body diagram for gear B, but it's the same magnitude. Torque, it's a moment, right? So it's force times RA, and then tau B is the same force times RB. All right? So since the force is the same, I can solve for F. And equate these two things. Okay, so I know that tau A over RA is equal to tau B over RB. And up here, I'd already derived an expression for the radiuses. Okay, actually, I guess I did. I avoided that. Okay, so let me quickly do that. Okay, so what we know is that 2 pi RA, that's the circumference of gear A, is going to be the number of teeth times delta x. Okay, so we can solve for RA and plug into the equation, and we would have tau A. RA is NA delta x over 2 pi. So I do that, NA delta x with the 2 pi on top. And we would have a similar expression for tau B. NB delta x 2 pi. So the 2 pi and the delta x cancel, and we have a different equation for torque. All right, so I can solve for tau B because that's the driven gear. Okay, so that's going to be tau A times NB over NA. Okay, so that's our torque equation, and so you see, if we wanted to know the torque for this particular problem, tau B is going to be the original torque, which is 5 foot-pounds, times NB. All right, NB was 20 divided by 10, and so the use of this gear translated the torque to make it larger. All right, so what was the trade-off? Well, the trade-off was the speed. The speed gets traded for torque. All right, so we have a slower speed, slower RPM, but greater torque. So I could take the same approach for gear C, where I take a look at the driving torque. The driving torque was 10 foot-pounds of torque, times the number of teeth on gear C, which is 30, divided by the number of teeth on gear B, which is 20. All right, so that works out to be 15 foot-pounds of torque. All right, so I notice also, oh, I forgot to erase that. I noticed also that I could have gone straight from looking at this problem, knowing the answers for, or knowing the torque provided at gear A, and using the gear ratios to find the total torque at gear C. Okay, so what I know is that I look at these cascaded gears and I have NB over NA times NC over NB. And when I plug in these numbers, I have 5 times 20 over 10 plus, not plus, times 30 over 20, and the 20s cancel and you get the 15 as before. Alright, so there's examples of simple gear calculations. I always think of this as a trade-off between speed and torque. Alright, if you want more speed, you got to give up torque. If you want more torque, you have to give up speed. Alright, so that's what our project's going to be about. The next video, we're going to talk about some practical considerations in terms of efficiency. All right, there's friction losses in these gears, and so that actually affects the amount of torque that we can provide. All right, so hopefully this helps, and we'll see you on the next video.